Welcome to the lecture titled Review of Time Domain Based Identification. In this lecture, we shall discuss about some issues related to time domain based identification. Also, using some statistical measures, measurement error effects on the model parameter estimations will also be described. This is the offline identification scheme we have already discussed earlier. Offline identification scheme. Why it is called the offline identification scheme? When the relay is switched on, that time the controller remains out of the loop, and when the controller is in action, relay remains out of the loop. That is why this scheme is known as the offline identification scheme. Then how identification is accomplished? The limit cycle waveform is obtained, and analysis of the limit cycle waveform results in 4 powerful analytical expressions. And now, solving the set of analytical expressions, it is possible to identify the dynamics of a real time process in the form of transfer function models. Now, the transfer function models can assume various forms. Now, that we will not discuss again, rather we shall see the limitations of this identification scheme. So, the major limitations of the offline identification scheme are: first, you need to solve a set of nonlinear equations using some nonlinear equation solver. So, a set of nonlinear equations are to be solved, and solution of the nonlinear equation requires you to choose proper initial values or initial settings while trying to solve the set of nonlinear equations. So, choice of initial solutions, are of paramount important, means choice of initial solutions are to be proper. Next, controller is to be switched off. Controller is to be switched off while conducting the identification test or relay experiment. That means, the process operation will get disturbed. So, when the controller is switched off, normal operation of the system, closed loop control system, is affected. Now, in the face of presence of static load disturbances, we may get inaccurate peaks, or the measurement of the limit cycle output may yield inaccurate measurements. So, static load disturbance may result in inaccurate measurements. And lastly, the measurement noise affects the estimation of the parametric models So, measurement noise results in inaccurate measurements and which in terms may yield higher estimation errors or the parameters may be estimated inaccurately. So, these are the 5 important limitations we have with the offline identification scheme. In spite of that, for each in analysis and for each in identification, offline identifications are often chosen or selected. Now, since measurement noise plays an important role, it will be nice to see the estimation errors resulting due to measurement noise. So, the presence of measurement noise leads to error in measurements, which indirectly gives identification error, and the identification errors can be quantified by using some statistical measure such as the standard deviation. So, the standard deviation for the estimation error can be given by this expression. What is that? Sigma q is equal to square root of sum of I equal to 1 to n del q upon del p I square sigma p I square. What are q, p and sigma? Sigma is the standard deviation. Now, q is a function of the parameters of the transfer function model. Sigma p I is the standard deviation of the variables. Those are there in the explicit or inexplicit expressions. Those are to be used for identification of transfer function models. Now, sigma q is the standard deviation of the estimated parameter, that is q. Let me give one simple example. Suppose some t is a function of theta by tau, let us say. Then how can I find the standard deviations? Now, sigma t will be equal to del t upon del theta square sigma theta square plus del t upon del tau square sigma tau square root. This is how we can find the effects of the parameters theta and t on the estimation value of capital T. Okay. So, this is how the standard deviations are found. Suppose theta is deviated by some value, tau is deviated by some value, then how much accuracy we have in the estimation of t can be obtained from sigma t or the standard deviation of t. So, using this, now we shall try to find the estimation errors associated with a first order plus date time model parameters. What is one first order plus date time transfer function model parameter? FOPDT model can be given in the form of GS is equal to k e to the power minus theta s upon T1 s plus minus 1. This is what we have already discussed earlier. Now, to estimate the parameters associated with this transfer function model, we have got some explicit expressions for T1 and theta, okay? And k can be found by some other technique or can be found from the measurement of the area of the output signal divided by the area of the input signal. Now, we have got expression for T1 H. T1 is given by plus T1 is given by minus plus tau divided by ln of kh minus plus ap divided by kh plus minus ap. So, this expression has already been derived in our earlier lecture. Similarly, the expression for theta is given as minus plus T1 times ln of kh minus plus ap divided by kh. When you get this type of expressions, when we use symmetrical relay test, symmetrical relay experiment is conducted, then the analysis of the limit cycle waveform results in explicit expressions of these forms T1 and theta. Now, as I am telling, due to the measurement noise, it is possible to get inaccurate values for tau, k and ap. These are the three measurements we are making. Now, assuming that k is also affected by the measurements of the ratio of output signal to the ratio of the input signal. Okay. So, let me find the standard deviation of T1 with respect to that of the tau or variations in tau, k and ap. So, let me start with the basic expression. T1 is given as minus plus tau divided by ln of kh minus plus ap divided by kh plus minus ap. Let us write this in the form of minus plus tau divided by ln x, where x is equal to kh minus plus ap divided by kh plus minus ap. Why I have written in this form? So that I will be able to find the partial derivatives conveniently. Now, how much will be the partial derivative of T1 with respect to the tau? This will be equal to minus plus 1 upon ln x, and ln x is how much? That is ln x from here can be obtained as, or 1 upon ln x, 1 upon ln x will be equal to T1 divided by minus plus tau. So, substitution of that will give us is equal to minus plus 1 minus plus times your 1 upon this is equal to T1 by minus plus tau. So, minus plus will cancel out, giving us T1 upon tau. So, this is what I get, one partial derivative of the variable T1 with respect to the measurement tau. Similarly, we can find del T1 with respect to del AP. Now, here you need to find this in the form of del T1 upon del x, because T1 is a function of x now. T1 is equal to minus plus tau upon ln x. So, I have to use this identity, del T1 upon del AP is equal to del T1 upon del x times del x upon del AP. So, del x can cancel out, giving us del T1 upon del AP. So, I need to find two partial derivatives to find the partial derivative of T1 with respect to AP. So, how much is del T1 upon del x? So, del T1 upon del x will be equal to minus plus tau times the differentiation of 1 upon ln x formula is to be used, which gives us minus 1 divided by ln x square times 1 upon x, and next we will find del x upon del a p will be equal to del x upon del a p times x, sorry, this will be del upon del a p of x. So, what is x? X is k h minus plus a p divided by k h plus minus a p. So, this is not difficult. Once you know the way partial differentiations are done, then it is very easy to find the partial differentiation. Now, we know that 1 upon ln x, 1 upon ln x from here, 1 upon ln x is nothing but t1 upon minus plus tau. So, I will make use of this. So, when you substitute this, then you get minus plus tau times minus 1, then you will have for this t1 divided by minus plus tau square into 1 upon x. So, 1 upon x means you will get k h plus minus a p in the numerator and k h minus plus a p in the denominator, because x is this much. So, 1 upon x will be the inversion of x. So, you will get this term. Now, let me find del x upon del a p, which is given by del x upon del a p will be equal to del of del a p times, what is x now? X is k h minus plus a p. So, k h minus plus a p divided by k h plus minus a p. So, it will give now k h plus minus a p times differentiation of this. So, that will give your minus plus 1 minus, you will keep k h minus plus a p here times differentiation of this will give now plus minus 1 divided by k h plus minus a p square. So, this is how you find the partial derivative of x with respect to a p. Okay. So, upon simplification now the numerator will give you minus plus k h, then it will be minus a p and here. So, minus of minus times plus minus 1 will be minus plus k h, then minus minus plus. So, it will give plus a p. Okay. So, this is how we get the numerator, where a p will cancel out and ultimately giving us an expression of the form minus plus 2 times k h divided by k h plus minus a p square. Now, finally, how much will be the partial differentiation of t1 with respect to a p? So, please substitute those expressions now, del t1 upon del x time del x upon del a p. So, the first part we have obtained as minus plus tau and then let me see, minus plus tau, then minus 1 times t1 by plus minus tau. So, minus 1 times t1 by minus plus tau square into k h plus minus a p. So, into k h plus minus a p by k h minus plus a p. So, all these terms are for the partial differentiation of t1 with respect to x. Now, when it is multiplied with the partial differentiation of x with respect to AP, I will get minus plus 2 kh divided by kh plus minus AP square at the end. Okay? AP square at the end. Now, kh plus minus AP in the numerator and here the power will go out. So, leaving us an expression of the form minus will come. So, plus minus it does not matter. So, plus minus tau times T1 upon minus plus tau square into minus plus 2 kh due to this term divided by, if you multiply now this and this, where the power has gone, kh minus plus AP times kh plus minus AP will result in kh square minus AP square. Please see the sign, minus plus will give minus, plus minus multiplication will give minus. So, ultimately it will be like a plus b times a minus b, giving us a square minus b square. So, finally, what I get, the final expression for this one will be equal to, is the final expression. Okay, no more simplification is required, or further simplification is possible, because tau square will come in the numerator denominator, cancelling this tau. So, I can get outright your T1 square. So, T1 square divided by tau times minus plus 2 kh by k square h square minus AP square. So, this is what we have got for the partial differentiation of T1 with respect to AP. So, similarly, the partial differentiation of T1 with respect to theta, sorry, we do not have theta here in the expression T1. So, the T1 expression has got 3 variables or 3 measurements, tau, k and AP. Therefore, I need to find the partial differentiation of T1 with respect to k, because k is now assumed to be measured. So, del T1 upon del k will similarly result, can be written as del T1 upon del x time del x upon del k, giving us the terms minus plus T1 upon plus minus tau square times minus plus 2 APH now divided by k square h square, or you can outright write in the form of kh square minus AP square, sorry, kh square minus AP square. So, this is our third expression. Now, the finally, the standard deviation of T1 is given by the expression del T1 upon del tau square sigma tau square plus del T1 upon del AP square sigma AP square plus del T1 upon del K square sigma k square root. So, this is how the standard deviation of the variable or the estimated parameter T1 is given in terms of the measurement tau, AP and k. Okay. Now, you simply need to make use of the 3 expressions we have found for partial differentiation of T1 with respect to tau, AP and k over here, to finally get it in the form of T1 upon tau square sigma tau square plus, for this one we will have 2 kh T1 square divided by tau times k square h square minus AP square times sigma AP square plus, for this one already when you take the square, how do you get this one? So, you have already got terms like 2 AP H T1 square divided by tau K square H square minus AP square sigma K square root. So, this is the final expression for the standard deviation of T1 in terms of the standard deviation of tau, AP and K. So, assuming that the measurements, what deviation means what? Basically, when I am measuring the half period, tau means what? This is the half period. Okay. When we have got a limit cycle of the form, this one, tau means this is the half period. So, when you make measurement due to the presence of measurement noise, there will be measurement error. We may not be able to accurately measure tau. So, suppose instead of measuring the correct value tau is equal to 10, if I measure tau by 10.05 or 10.1, then we have got the measurement error. This will lead to the standard deviation in tau, okay? And that results in the standard deviation, deviating from the actual value or the accurate value. So, how much inaccuracy there is in the estimation of the parametric model T1 can be quantified using this expression. Okay. So, this is how the estimation errors are quantified using the statistical measure standard deviation. Similarly, let us go to the other parameters. So, this is the final expression that we have got, where this will be T1 square and this will be tau. Okay. I have made some mistake here. So, now it is correct. Then this is what already we have derived. Similarly, allow me to derive the expressions for that of the other parameter associated with the first order plus dead time model. So, theta is given by minus plus T1 times ln of Kh minus plus AP divided by Kh. Then how can I get the partial differentiation now? For that, take this as minus plus T1 minus plus T1 times ln x, again where x is given by now Kh minus plus AP divided by Kh. Then to find the what are the parameters associated in this explicit expression for the time delay associated with the first order plus dead time model, we have got T1, we have got K and we have got AP. These are the three variables that are going to affect the estimation error. Okay. So, I need to find del theta upon del T1. So, del theta upon del T1 will be how much? This will be equal to minus plus ln x. Okay. So, this will be minus plus ln x, because you are differentiating with respect to T1. So, ln x is how much? Theta by minus plus T1. So, that way I can write this by theta by minus plus T1. So, we got one partial differentiation of theta with respect to T1. Now, another partial differentiation of theta with respect to the variable del AP can be obtained in the form of again del theta upon del x times del x upon del AP. So, please use this to find the partial differentiation. Now, del theta upon del x will be minus plus T1 time differentiation of ln x is x, sorry, differentiation of ln x is 1 upon x, only. So, giving us 1 upon x. This is for the first term. What about the second one? Del x upon del A p will result in del x upon del A p will be del upon del A p times k h minus plus A p divided by k h. So, it will be minus plus T 1 times inverse of x will give you k h divided by k h minus plus A p. Now, the differentiation of this one will give you k h times differentiation of this with respect to A p will result in minus plus 1 minus k h minus plus A p times differentiation of k h will be 0. So, the second term is ultimately 0 divided by k h square. So, when you simplify this k h square, power will go out, minus plus multiplied, that will give you plus. So, I will be left with an expression of the form T 1 k h in the numerator and divided by this k h again will cancel out. We have got k h here. So, k h will go out. So, in the numerator I will be left with T 1 only. So, finally, del theta upon del A p will be T 1 upon k h minus plus A p. Okay. Now, let us try to find the partial differentiation of theta with respect to k similarly. So, in this case del theta upon del k will be equal to again minus plus T 1 time 1 upon x, like the earlier case it will be 1 upon x into del x by del k is equal to minus plus T 1 into k h by k h minus plus A p into del of k h minus plus A p divided by k h upon del k. So, now the differentiation is to be found with respect to k. So, simplification will give now k h upon k h minus plus A p. This differentiation how to find? We can find this like the earlier case k h time differentiation with respect to k. So, it will leave as h then minus k h minus plus A p times differentiation of k h with respect to k, it will leave us h divided by k h square. So, I will cancel this, giving us minus plus T 1 divided by k h times k h minus plus A p into the numerator of the last expression. So, how much it will be? K h square minus k h square minus is there, therefore, we will be left with plus minus A p h. So, you have got A p h finally, and due to this minus plus multiplication of minus plus with plus minus, you will get a minus here, leaving us in the numerator minus T 1 A p h divided by k h minus plus A p. So, further simplification can be obtained, leaving us minus T 1 A p divided by k h minus plus A p. So, this is how the third partial differentiation is obtained for finding the standard deviation of theta with respect to the measured quantities. Now, I will write the final expression. So, sigma theta will be del theta upon del tau square plus no tau is there, T 1 is there, del T1 square time sigma T1 square plus del theta upon del AP square times sigma AP square plus del theta upon del K square sigma K square root. So, when you substitute the partial differentiations found earlier, we get the final expression H sigma theta is equal to square root of theta sigma T1 upon T1 square plus T1 sigma AP divided by KH minus plus AP square plus AP T1 sigma K upon K times KH minus plus AP square. Thus, the standard deviations are found. So, what benefit we get from finding the standard deviations? Basically, we have been able to find sigma T1 and sigma theta for the first order plus dead time model given by GS is equal to K e to the power minus theta s upon T1 plus minus 1. Okay. So, when there are measurement errors in the measurement of half period tau, the peak amplitude AP and the steady state gain K, then the estimated parameters will be subjected to standard deviations of sigma T1 and sigma theta. Okay. This is how it is possible to quantify the measurement errors or quantify the estimation error, I would like to say estimation error in terms of the standard deviations. Okay. So, this is how one can quantify the estimation errors associated with the measurement errors particularly, or with respect to the measurement errors, the errors in estimation of K, theta and T1 and particularly theta and T1 can be evaluated. Next, we will go to the online identification technique, because the lecture is on review of the time domain based identification techniques. So, in the online identification scheme, we have used frequency domain analysis earlier, but not necessarily one has to go for frequency domain analysis, although for ease in analysis of the relay control system, the describing function based frequency domain analysis has been used earlier. In today's lecture, we will see how time domain based analysis can be extended for online identification of processes. Now, the online identification scheme with the help of a relay with hysteresis, will be described very briefly. Okay. So, this is an online identification scheme, because the controller remains in operation throughout the operation of the process, even during identification of the process. Therefore, this scheme is known as the online identification scheme, and we have a hell lot of advantages compared to the offline identification scheme we have described earlier. Now, let the process dynamics be described by a transfer function of the form GPS is equal to K e to the power minus theta s upon tau s plus 1. So, please do not confuse. Now, the tau here represents the time constant of the process, time constant of the process, not the measurement parameter. Okay. Similarly, the PI controller that is employed in this online scheme has the form C 0 S is equal to KCO plus KIOS. Why the subscript O is there? That is for initial value when you are conducting some relay test or experiment, and after relay test and experiment, then the C or the controller will be CS. Okay? I believe you have followed. So, at the time of relay test, the controller dynamics is given by KCO and KIO parameters, with the help of KCO and KIO parameters. Now, if you draw the equivalent circuit diagram of this block diagram, then what relay is basically? So, the relay will be subjected to, this is your relay with hysteresis, then you will have the process GS, negative feedback, and you have got the controller C0S present here. Okay. So, the relay is basically a dynamics of this form. So, fictitious transfer function model, which the relay is becomes Ys upon U1s. Where is U1s? U1 is here. Okay. Then the transfer function between y and U1 can be expressed in the form of k e to the power minus theta s upon tau s plus 1 plus k KCO e to the power minus theta s plus k KIO upon s e to the power minus theta s. So, what benefit you are getting from this fictitious transfer function model? This helps in the identification of the system in time domain. In place of using the frequency domain, I can use the state space analysis for identification of online identification of the system. How the state space model of this fictitious transfer function model can be found? So, the state space model or state space equations can be obtained H given y s upon u 1 s H k e to the power minus theta s upon k e to the power minus theta s upon tau s plus 1 plus k k c o e to the power minus theta s plus k k I o divided by s e to the power minus theta s. Now, cross multiply and write the expression in the form of the differential equation giving us tau y dot t plus y t plus k k c o y t minus theta plus integration of k k I o y t minus theta dt is equal to k times u 1 t minus theta. So, this is how when you cross multiply these terms and take the inverse Laplace transform, we get the differential equation of this form. So, let x t the state variable be y t, resulting in an expression of the form tau x dot t plus x t plus k k c o x t minus theta plus integral of k k I o x t minus theta dt is equal to k u 1 t minus theta, implies x dot t. So, let me introduce one variable. Suppose lambda is equal to minus 1 upon tau. In that case, x dot t can outright be written in the form of lambda x t, then these terms will go to the right half. So, that way you will have plus lambda k k c o x t minus theta plus lambda k KIO integral of x t minus theta dt plus no, there will be minus, because this lambda is minus 1 upon tau, it is getting divided. So, minus k lambda u 1 t minus theta. So, this is the state equation we are getting from that fictitious transfer function model, and the output equation is given by y t equal to x t. Now, using the state and output equations and the limit cycle waveform, then now it is possible to find analytical expressions for the zero crossings and for the peak amplitudes, and how to find the expressions for zero crossings and peak amplitudes have been described in our earlier lectures. Okay. Only you need to make use of this state equation and this output equation in place of the earlier state and output equations. Okay. This is how from the measurement of the peak amplitude and half period and so on, it will be possible to estimate the parameters of this transfer function model, and the parameters of this transfer function models are k, tau and theta. So, this is how I can make use of time domain analysis for online identification of systems. Okay. Next, we shall go to the extension of the time domain analysis to nonlinear processes. So, how can we make use of the time domain analysis, state space based time domain analysis for estimation of dynamics of nonlinear processes? So far we have discussed about, or we have studied about the identification of linear processes. Now, the time domain analysis can also be used to identify nonlinear dynamics. Now, the relay is having some hysteresis. You look at the relay. So, let the hysteresis of the relay be given by epsilon. Then it is possible to conduct relay test like this, and the nonlinear process dynamics can be represented by a linear dynamics given by Gs along with some nonlinear function. The nonlinear function can have static nonlinearity, can have dynamic nonlinearity. Okay? Or now, the nonlinear process dynamics can be given in two forms. The nonlinearity can appear first, and then the process dynamics or dynamic model can be given later. So, these are the two ways one can get the block diagram representation for the nonlinear process or the models for the nonlinear processes. Now, how can you estimate, how can you find, ascertain that you will go for identification of linear system or nonlinear system? Now, as I have already described, when the nonlinear system dynamics is given by this model, then we get some Wiener type model. This is called Wiener type nonlinear process model for nonlinear dynamics associated with a system. And the second type of representation of nonlinear dynamics in the form of block diagram is known as the Hammerstein type. Okay? Now, relay test is conducted with the relay having hysteresis, and one parameter AU is measured. What is AU? Now, AU is equal to H times T plus minus T minus. So, what are T plus and T minus? T plus and T minus are the width of the limit cycle output signal. For positive output, you get this as T plus, and for the negative output, the time from here to here, the next zero crossing is shown by T minus. So, using this information, when AU is equal to 0, then you can go for identification of a linear process model. When AU upon H, what is H? H is the relay setting, and epsilon is the hysteresis with width associated with the relay. So, when this is satisfied, go for identification of an winner type model, and when this is satisfied, go for identification of a Hammerstein type model. Okay. So, this is how nonlinear process are identified. Now, let me summarize the lecture. Now, time domain based techniques can be extended for offline identification, can be used for online identification, and also can be used for identification of nonlinear process models. This is what we have not studied in any lecture so far earlier. Now, further, accuracy in estimation of model parameters can be quantified for simple process models like first order plus date time transfer function model using some statistical measures such as standard deviation. So, standard deviations or the sigmas. Okay. And lastly, any point to ponder? Should we go for time domain based identification or frequency domain based identification? So, we have studied two types of identification during our last lectures, where we have seen that one can make use of time domain based identifications and frequency domain based identification. Out of the two, although frequency domain based identification is quite easy or easier compared to the time domain based one, time domain based identification results in more accurate estimations, of the transfer function model parameters, whereas frequency domain based identification techniques are subjected to identification errors or estimation errors, and frequency domain based identification using describing function are subjected to erroneous results, because the describing function itself is an approximation. That is all in this lecture. Thanks.